Alright, so let's start by considering a nilpotent operator. Let T be a nilpotent operator on V. Okay, then we already know that all the characteristic roots of T are equal to 0. Zero is the only characteristic root of T, in the sense that 0 will appear as a multiple root as many times as the dimension of V, but there is only one distinct characteristic root, and that is 0. So the sum of all the characteristic roots is also 0, that is, the trace of T is equal to 0. But if T is nilpotent, then any power of T is also nilpotent. For all positive integers I. So if you take I equal to 1, you are just getting your T. But T square, T cube, these are also nilpotent. Hence, all of them have 0 trace. Now say we think of the converse. If this is true for all possible values of I, and it's not given that T is nilpotent, so what is given is that T is a linear operator such that the traces of T to the power I, for all positive integers I, are equal to 0. Is then T nilpotent? We can think of this converse. It's not true in general. Let us see why. You think of this operator, or rather this matrix, 2 by 2 matrix. Let F be a field of characteristic 2. Let A be this matrix, the 2 by 2 identity matrix. Now this matrix, and let us also assume that it's an element of F2. Okay, so our 0 and 1, these entries are coming from this field. Then what is trace of A? Trace of A is the sum of its diagonal elements, which however is 0 in this field. In this field means in this field. Also, any power of A is equal to A itself. So, this is true. Traces of these powers are also equal to 0. But clearly A is not nilpotent, because we have seen just now that this is A itself, which is not the 2 by 2 zero matrix. So T is not nilpotent. Let us also note that F has characteristic 2. However, if one assumes that F has characteristic 0, then the converse is true. And this is our lemma 683, and we are now going to prove it. So let's see. So now we have this. F is a field of characteristic 0, and V of course is some finite dimensional vector space over F, and T is a linear operator on V. As usual, T is an element of this operator algebra, such that the traces of all these powers of T are equal to 0 for all positive integers I. Then T is nilpotent. So the proof starts by considering the minimal polynomial for T. Let the minimal polynomial for T over F be this. And in this regard, let us also recall that when we say the minimal polynomial, we mean that unique monic polynomial which has the least possible degree, non-zero polynomial of course, which T satisfies. Okay, that monicness, you see, the actual definition of minimal polynomial does not give us a unique polynomial. It only tells us that it has to be a polynomial which T satisfies, and also it must have the minimum possible degree. But on top of that, if you assume that the polynomial is monic, then you get only one such polynomial, a unique polynomial over F be this polynomial plus alpha 1 plus alpha m. Okay, so if you substitute T for x, it will give you the 0 operator. That means we are going to get this T to the power m plus alpha 1, T to the power m minus 1, and so on, plus alpha m minus 1 T plus alpha m. You see, you can, if you want, you can simply write alpha m, but because we do not want to get confused later on when we see these things, I am going to write 1 here, and this 1 is the identity operator on V. This is equal to 0. This 0 is the 0 operator on V. Alright. Now, taking trace on both sides, and taking trace and recalling that trace is a linear function. Linear function means the trace of this left hand side will be equal to the sum of the traces of the individual terms in this sum. And there also, for example, say the trace of alpha 1 times T to the power m minus 1 will be equal to alpha 1 times trace of T to the power m minus 1. The scalars can be taken outside. That is also a part of linearity. So we can at once write this. Trace of T to the power m plus alpha 1 times trace of T to the power m minus 1, and so on. Do you remember where this linearity of trace is coming from? It's coming from our previous video where we have that lemma which has three parts. The first two parts give us linearity and the third part says that trace of AB is equal to trace of BA. That thing, that result. M minus 1 times trace of T plus alpha M times trace of 1 equal to trace of 0. Now this will imply what? Now we are going to use the fact that the traces of all these positive integral powers of t are equal to 0 because that is the hypothesis. That means these terms are going to be 0. 0 what? 0 real, well, not necessarily real number, I mean the field element 0. 0 of the field f. So these terms won't really give us anything. What about this trace, this last term? The identity operator, when you express it as a matrix, you get the identity matrix which has ones along the main diagonal. So the sum of those ones is n, provided, and the 0 operator, of course, if you express it as a matrix, you will get the 0 matrix. So the sum of the diagonal entries is 0. But what is this n? This n is the number of elements you have in the diagonal, or in other words, the size of the matrix. It's also the dimension of our vector space, where n is the dimension of V. Now we use the fact that this equation is an equation in F, and F has characteristic 0. Because this dimension n is a positive integer, you see, you recall that in all our discussions, in the very beginning itself, where we started studying operator algebra, we assumed that we won't really consider the 0 vector space whose dimension is 0. All our vector spaces will be finite dimensional and will have a positive integer as their dimension. So that is why n is a positive integer. Combined with that, the fact that f has characteristic 0. So this can happen only if and only if this alpha m is 0. Since f has characteristic 0, this implies that alpha m is 0. But what is alpha m? Alpha m is the constant term of the minimal polynomial for t. And when that becomes 0, you know that a previous result tells us that t is a singular operator. It's not regular. It's not invertible. And that result is theorem 612. By theorem 612, t is singular and hence has 0 as a ch root, as a characteristic root of it. That means we have now concluded, after all these things, that t has the characteristic root 0. Now, as a root of the minimal polynomial, t may occur more than once. Okay, so that possibility is there, but at least once it will occur, and that's what we need. So now what we do, the field f, although it has characteristic 0, it may be like the field of real numbers, which is not algebraically closed. If you have a polynomial equation over an algebraically closed field, then the roots will lie in that field itself, like we have the field of complex numbers. F may be like R. So instead of F, we now have to choose an extension of F in which all the roots of the minimal polynomial for T will lie. So we have to consider the splitting field of the minimal polynomial. Now, consider T to be an element of this algebra instead, where in place of F we now have K, where K is the splitting field of Px, the minimal polynomial for T. Okay, now let us recall another result, and that result is theorem 641. It tells us that if we have a linear operator on a vector space V, all of whose characteristic roots lie in the underlying field K, then the vector space has a basis in which the matrix of the operator is a triangular matrix. We already did this, we proved this fact, and we are now going to use it. It is theorem 641. By theorem 641, V has a basis. In order to emphasize that this is happening over K, we write so. V has a basis over K in which the matrix of T is of the following form. That means the matrix will be a triangular matrix. Upper triangular or lower triangular, both are possible. The author has chosen lower triangular matrix, for which the upper triangular half consists of only 0 entries. So this is how we can have the matrix 0, 0, 0, 0, beta 1, alpha 2, beta n, and then alpha n, and the matrix has also been divided into blocks for our convenience, so that we can clearly see what's going on and we can use the blocks to say something. Alright, so why is the matrix like this? You see, we have already said that by this theorem, the matrix of T in that basis will be triangular, and we have chosen a lower triangular matrix. Okay. Additionally, we concluded moments ago that T has 0 as a characteristic root. Also, we know something else about triangular matrices, that when you express a linear operator as a triangular matrix, then the operator's characteristic roots appear along the leading diagonal of the matrix. So one of those diagonal entries has to be 0. Now the basis in which this matrix looks like this may have some vectors like this, say these characteristic vectors v1, v2, vn. There will be n vectors because the vector space is n dimensional. Now if you just simply consider a basis like this, okay, according to how the vectors are appearing, in what order they are appearing, that will decide where along the main diagonal these characteristic roots will appear. A characteristic vector corresponding to this characteristic root 0 may actually lie somewhere in the middle. Okay, I mean 0 is not here, say this is something, some characteristic vector corresponding to the characteristic root 0, and it's there somewhere in the middle. Then if you express the matrix of T, if you write the matrix of T in this basis, then 0 won't appear here, it will appear here somewhere. So then how can you bring 0 here? That's easy. Whatever characteristic vector corresponds to 0, you just change its place with whatever is originally appearing in front as the first vector. The resulting set is just like the original set, only the order has changed. It will still be a basis, but this time with this slightly modified basis, because see these bases are actually ordered bases in which it matters where each vector appears, that order matters. So in the new ordered basis, 0 will appear here. Okay, so that's how we really, in any situation, we can have the matrix like this. Okay, now the way we have divided it into compartments, we have 4 blocks, 1, 2, 3 and 4. You see this star indicates that below the main diagonal there are some entries. We need not write those entries, but above the main diagonal these are all 0. Actually the entire matrix has this entire thing as its diagonal. So because it's lower triangular, so the upper part has to be 0. The lower part may have some 0 entries, and additionally this one is also 0. Okay. Now if we write this as a block matrix, I mean this itself is a block matrix, but say in short, then it will look like this. Where T2 is this matrix. And it's an n minus 1 by n minus 1 matrix. Now, what do we know about the original t? We know that the trace of t to the power I or t to the power k is equal to 0 for every positive integer k. The advantage of having this type of block form is now this. This is what we have. Taking the kth power of t, where k is some positive integer, will give you this. When you work with block matrices, the blocks behave like ordinary entries. For example, if you multiply two such block matrices where the blocks are of appropriate size, say you have something like this, A, B, C, D times A prime, B prime, C prime, D prime, where these are not individual field elements but they are arrays, they are blocks. Then you can apply your usual matrix multiplication rule, A times A prime plus B times C prime. And the other entries also follow that rule. Here the product of A and A prime is matrix multiplication because A and A prime are also matrices. So that is the advantage you have when you can divide a matrix into block form and then multiplication is possible. That's how this is coming. So, I need to write for every positive integer k. Now, if you take the trace of t to the power k, then you have to take the trace of this matrix, this entire matrix, which is the sum of all the diagonal entries. One of those diagonal entries, because this is 1 by 1 block, will just be 0 plus the sum of the diagonal entries of this power of t2. That is why the trace of t to the power k will be equal to the trace of t2 to the power k. And this star and this star in general are not the same. Okay, this will change, but we don't need to really know how, because we are interested in only diagonal entries to calculate trace. But this is 0. For all positive integers k. Now, whatever argument we went through for t, we can also repeat for t2, because t2 now also satisfies those exact conditions, that the traces of all its positive integral powers are equal to 0. We can repeat the above arguments for T2 to conclude that it has 0 as a characteristic root. Okay. Well, you may say that that's not exactly like T, because T is a linear operator whereas T2 is a matrix. But when you are working with linear operators and matrices, I mean, they are the same. On one side you have operator algebra, on the other side you have matrix algebra. They are isomorphic. So if you do not change the isomorphism, if you fix the isomorphism by choosing some basis of the underlying vector space, then you can use operators and matrices interchangeably according to your convenience. So that's how you get again that similar conclusion that T2 has 0 as a characteristic root. Now we recall a previous exercise that we saw in the third section where we introduced matrices of this chapter. It says that for a triangular matrix, its characteristic roots are its diagonal elements. T2 is a triangular matrix. You can see that here. That means these are the characteristic roots. So one of these characteristic roots has to be equal to 0. And the exercise I am talking about is, I hope I have the number here, yes, 28. Section 6.3, one of these alpha i's has to be equal to 0. For some I. Not necessarily 2, but we can assume without loss of generality that I is equal to 2. If not, you know what to do. In place of T2, you can write another matrix in which you just change the positions of this 0 characteristic root with the first one, okay, with alpha 2. And you know how, because I have already said that about the linear operator. Without loss of generality that I is equal to 2. So besides the first characteristic root, see this alpha 2 is actually also a characteristic root of our original operator T. So alpha 2 also is 0. Continuing like this, we get all of these alphas equal to 0. But now T is being represented by a triangular matrix where all the diagonal entries are 0, and we know something about such a matrix. And that thing comes from another exercise, exercise 30. It says that the nth power of that matrix, of such a triangular matrix where all the diagonal entries are 0, if you raise it to the nth power, where n is the size of the matrix, you get the 0 matrix. So the matrix of T has its nth power equal to the 0 matrix. That is happening in the matrix algebra. An exact corresponding thing will happen in the operator algebra. That means T to the power n will be equal to 0. So we directly write this, and that gives us the conclusion that T is nilpotent. That's what we wanted to prove, right? After this, there is one lemma which is kind of technical, but the author says that it will help us in later results. It is named after Jacobson also. It is this lemma. We have heard about Jacobson radical in ring theory. I don't really know whether it's that same Jacobson. Maybe. So this lemma says this: if F is the field of characteristic 0, and S and T are linear operators on V over F, and they are such that the operator St minus Ts commutes with S. Okay. Seems like an ad hoc condition, but let's see where it takes us. Then St minus Ts is nilpotent. The underlying field has characteristic 0, so the guess is that the previous lemma will be used in its proof, and that's true. We use that. So if we want to use the previous lemma, what shall we need besides having a field of characteristic 0? Namely that all positive integral powers of St minus Ts have trace equal to 0. So let us take a positive integral power. Let k belong to the set of natural numbers. Recall that in this book, this set represents the set of all positive integers. Now, okay, the way this calculation goes, I think it will be more clear if I consider the case k equal to 1 separately. Oh, then I have to start it also a little differently than how it's given in the book. Note that trace of St minus Ts, recall that trace is linear, so this becomes trace of St minus trace of Ts, and that you know is 0, because by that lemma, our first lemma, St and Ts have the same trace. So at least this first power of the operator has trace equal to 0. Now let k greater than or equal to 2 be any integer. I need a little ink. Just give me a moment. So we are now going to consider the kth power of St minus Ts, and then we are going to calculate the trace of that kth power. We have Let us first consider the power itself. And the power can be written like this. Actually, we could have included this special case here itself, but anyway, okay, not a problem. St minus if you are thinking from an application point of view, because people are so obsessed with applications, and especially if that application is outside mathematics. Operator algebras have applications in quantum mechanics. Okay, the mathematics of quantum mechanics is functional analysis and operator algebras. TS. Now, what was the hypothesis? The hypothesis is that St minus Ts commutes with S. So, any positive integral power of St minus Ts automatically would also commute with S. In particular, this power would commute with S. So, in place of this product, you can write S times this. That's what we are going to write next. Minus in order to better see what we have here, we will give this product a name. Say we call it B, BT. So you can see that, well, what the hell have I written? No, it's not BT, but I should give this product a name. Okay, yes, SB, because then you have B here as well, and you get BS. Now I think it's clear what's going to happen. So trace of this is equal to trace of SB minus BS, which is trace of SB minus trace of BS, and that's equal to 0. So we have actually proved that the trace of any positive integral power of St minus Ts is equal to 0. And that is why by the previous lemma, St minus Ts is nilpotent. By the previous lemma, in classical physics, you work with mostly with constants, variables, equations involving these things. But for some reason in quantum mechanics, in quantum physics, you need operators associated with physical quantities like energy operator, momentum operator, and the characteristic roots of those operators have special significance. In some situations, the variable can only take those values. Okay. So, at one point, if we are able to start studying quantum mechanics, there we will see how these things are used. But that will be all for today. And tomorrow, what do we have tomorrow? I think analysis. Whatever it is, so we will see tomorrow. Until then, this is me, Lucifer from A Mathematical Room. Have a nice night.